Hey folks, so I promised you a video and some extra resources to try to help us visualize and understand these volumes of rotation. So I went ahead today, I spent some time writing up a little bit of code. This is using a program called MATLAB. Um, a lot of the people in the math department like using MATLAB. I love using MATLAB. It's actually what I use for my own research. I'm happy to share this code with anyone if you'd like to play with it. And I could teach you how to, run this code. It does require the MATLAB program, which you can use on campus for free. I can teach you these things. But for this video, let's just go ahead and use this to try to visualize some of these surfaces of, or these volumes of rotation. So on the left, you see I have a plot of the square root of x. So I'm going to try to use some of the same examples from what we did in class. So on the left is the graph of square root of x, and this is that blue line. And I'm going to rotate it around the red dotted line, which is the x-axis. Okay, so if I hit a button, on the right, you see this process happening. And I even included, you can see these little red discs, these circles, which give us a visualization of those cross sections of that volume. Okay, it's not all of them, of course, but just just a couple of individual slices to help us see what that looks like. So you can see I've taken that square root of x function, I've rotated it around that axis, and what I get is this nice sort of rounded cone shape. If you look at it from the side, right, I mean, from the side view, you can see that profile, that square root of x profile on the top and the bottom. And what I've done is rotating it around, you get these beautiful discs in the middle. Okay. And so what we want to note is that the radius of any of these discs is the distance from the x-axis up to the square root of x function. And so when I calculate the area of the circle, the radius I would use is just, well, the radius is square root of x. It's the function itself, okay? The distance from x-axis up to the outer part of this shape. Okay, let's go ahead and try maybe not the square root of x, or actually no, I'll leave the square root of x, and maybe I'll change the axis of rotation just for, practice. So I'm going to rotate it now around, okay, the line -1, y equals -1. So I'm using the same function, square root of x function, but now I'm going to rotate this around a different axis, the y equals -1 axis. Okay, so take a moment, try to visualize this in your head, what you think this will look like, what will change from the last example to this example. And let me go ahead and run it, and we can see what we get. Oh, no, I made a coding mistake. Sorry, ignore this. That's on me. I need to do one quick thing here. I forgot to do technical issues here. Okay, let's go ahead and do that now. Okay, so now I'm going to rotate. There we go. Okay, and now what do we get in this case? Well, we still get these disks, it turns out, right? And that's because I'm rotating this graph, around this dotted line, and I'm filling in all of the area beneath this, and then rotating it around. And what I get on the right is, yeah, some of these disks. Now, what is different now is what's the radius of these disks? Okay, it's not going to be square root of x this time. Let me take a look at the side profile. You can see it's similar looking shape. It's a little bit different of a shape. But if I look at that side profile, what you'll notice is what is the radius of any one of these disks? Well, the radius should be the distance from the dotted line up to, let's say, the top. Well, from the top to the black line, well, that's the distance here from the top to the black line. That's f of x, that's square root of x. But that's not the actual radius, right? The actual radius of my circle is this distance plus another one, representing the distance to that dotted line. Okay, so if you look at the figure on the right here, if I look at one of these disks, we see the radius f of x down to the x-axis, down to -1. Okay, so that radius is f of x, so square root of x, plus an additional 1, okay, that I have to make up. Okay, so the radius here is different because I rotated around a different axis. Okay, let's try another example. Now let's do one where, okay, I'll do, let's say x for my outer, and I'm going to do x squared. You can ignore this part. Sorry if you don't know what's happening with this code. Looks a little confusing. Okay. Okay, so now what I'm going to do is, I think this was maybe example 5 or so that we did together. Now I'm going to rotate this region, which is, yeah, from 0 to 1, I have the line y equals x, and I have the line y equals x squared. And I'm going to rotate this around the x-axis. Okay, so you see that red dotted line representing where I'm going to rotate. And okay, let's go ahead and do that. And you can see the picture I'm getting is a little bit different. Because as I'm rotating that section around, you see what's happening is I'm getting a different shape, right? I'm getting washers this time because I'm not filling in all of the space to the red line, right? I'm not up to these graphs. I'm filling in just a section of it. And so that means when I rotate that section around, I get a ring, not the full circle. Okay, so it's what we call a washer, not a disc. Okay, so as this is finishing up, let's start moving this around a little bit so we can get a visualization of what this looks like. I'm not filling in the entirety of the inside, right? I'm just giving you a couple of these typical cross sections, right? So it's easier to see through it and around it. Okay, but you can see from the side view, right? You can see that profile matching up, right? I have this top line, the outer part representing the y equals x, sort of an inner curve for the x squared. And that sort of, yeah, the in between those two regions, you get sort of these nice rings that give you the volume we try to calculate. Okay, so if I want to know the cross-sectional area here, I need to again calculate the area of the circles. Well, I have two circles now. I have an outer circle, and I'm going to subtract the inner circle area. And so in this case, what is the radius of that outer circle? Well, it's the distance from the red line up to the top, so that straight line. And so that's the distance from this red line up to the line y equals x. And then I subtract from that the area of the inner circle, which is from the x-axis up to this inner region, right? So that inner curve. And so that's what gives me the distance from the x-axis to x squared. And so that's why in class we had the expression pi times x squared minus pi times x squared squared. That was the outer area of the outer circle minus the area of the inner circle. Okay, but really the focus here is just being able to really try to intuit that visualization here, right? This very interesting sort of, these rings that kind of come together, these washers. Okay, let's do the last one. This was one of the hardest ones we did in class. We're going to take the same two functions. We're going to rotate this around a different axis. Rotate this around the axis -1, y equals -1 again. Okay, so same two functions. It got scaled a little bit, right, from the visualization, but now I'm rotating around a different axis. So again, I'm going to imagine sort of the region between these two curves is going to get rotated around. Let's go ahead and try to visualize. Okay, so you see what's happening here. We still are getting washers, right? We're still getting washers. And it's because, right, I'm not filling in all of the distance between the red line and the curve itself, the functions themselves. So I'm going to have just a small region that gets rotated around. That's what gives me these ring shapes. And okay, so as this finishes up, we can start moving it around, starting to get some intuition. So here we go. I'm going to put you on the side here so you can try to compare the starting picture, and you can see some similar shapes on the right-hand side. As I rotate it around, you can kind of take a look at those washers and see how they're, stacked next to each other. And I'd want to calculate the area if I had all of those filled in, or so the volume, sorry, of all of these put together. And so now let's take a moment again and let's try to understand the radii of these circles. Okay, so calculate the area of these washers. So again, the radius of the outer circle would be going from the red line up to the very tippy top. Okay, and so that's really what's the distance from this red line up to this line. And that distance would be, well, this is the line y equals x. So y equals x will get me from the black line to the function. And then I need to add 1 to that to get my actual radius. Okay, so that's why we would write in class, the radius here is x plus 1. Okay, and what about the inner circle? Well, it's going to be a similar story, but now I'm going up to that inner curve, which is the x squared curve. And so now my distance will be x squared. That gets me from the top function to the black line. So x squared plus 1, the plus 1 is what gets me down to that red line. Okay. So all of these visualizations, these are really just for the dx integrals, right? So integrating cross sections that are going across left to right. Okay, you have to forgive me that, in one day I couldn't come up with a quick program to do both this and the dy integrals. But of course, I certainly encourage you to practice visualizing these for the dy case as well. It should be a very similar thing, just kind of flipped vertically. Again, if anyone wants to play with this, please let me know. I'm happy to show you how this works in office hours. If you have any other questions about visualizing, about why things are disks or washers or how we're calculating area, do let me know. But I do hope this was helpful. I hope that this clarifies some of the questions we had today about how these things should be visualized. And if it's still confusing, don't be afraid to come and talk to me about it. Let's spend some more time talking about how to visualize. All right.